Hello and welcome to the next video in my series on basic statistics. If you are new to the channel, welcome. It is great to have you. If you are a returning viewer, it's great to have you back. If you like the video, consider giving it a thumbs up, sharing it with classmates, colleagues, or friends, or anyone else you think might benefit from watching. I will also note in this video that there is a GoFundMe link in the description. I use those donations for one purpose: to get these videos professionally closed captioned. Now I know not everyone can contribute, but if you can, consider doing so. Every dollar equals 1 minute of captions, and that will help everyone else who have used these videos on YouTube for free. So all that being said, let's go ahead and get started. So this video is the next in our series on simple linear regression. Now this is a topic not many people think about, and that is the idea of outliers and influential observations in our data. And it's very important because outliers and influential observations can affect our model significantly. And this is true for even more complex forms of regression and other techniques like machine learning. All it takes is a few data points that are outside the norm to influence our model one way or another. So let's go ahead and learn about outliers and influential observations in regression. Before we do that though, I want to pause just for a second. I am an educator, and I love seeing other educators do things that really make a difference in the lives of other learners. I'm not being paid to say this. I am not been asked to say this or anything. I'm doing it on my own. And I want to point out a book that's been released recently that I really think changes the game for those wanting to get a grasp on machine learning. And that is the 100-page machine learning book by Andrei Burkhoff from Gartner. And this book really changed the way I learned about machine learning. I'm not a mathematician or anything, and I really like someone to take these complex ideas, boil them down for me, and explain them in a clear, concise way so they actually get the underlying concepts. And this book has done that. And I've read through it. I'm going to go through it again. And as an educator, again, as a teacher, I look for things that are game-changing. And this book is that interface for people that are just wanting to get into machine learning and understand those basic concepts. So I highly recommend, if you're interested in this, to go ahead and pick up this book. There is a link in the description below that'll take you right to it on Amazon. Just make sure if you do buy it, you buy it from Amazon. That way the author gets full credit. So again, please check out this book if you're interested in machine learning. And that being said, we'll go ahead and get into the video. So let's talk about outliers and influential observations in regression. Okay, so here is a scatter plot and regression line of some data I pulled off the internet myself. And each data point here represents a used car. More specifically, a used Toyota Camry SE sedan here in the US. So what I did is I collected the data and then plotted it on a graph and then put a regression model on it, simple regression. So along the x-axis here at the bottom, we have the number of miles that are on the car, so the odometer miles. On the y-axis on the left, we have the selling price for the used car. So we can go ahead and model this using regression, and we come up with a model here at the top. The only thing that's important here is the slope of the coefficient, which is negative 0.0937. So based on this model, what that's telling us is that for every mile a car is driven, it decreases in value by 9.37 cents, okay? Because that's dollars. So it's $0.0937, which is about a little bit over 9 cents. So every mile it's driven, the car decreases in value by 9 cents. Now our R squared, which represents the amount of variance in the price that is explained by the mileage on the car, is 0.2963. So about 30% of the variance in the price is explained by the number of miles on the car. Now, if we look up here on the right, we have this blue diamond. What is that? This is part of our data set, not an error on the slide, but what is that? And that's what we're going to talk about in this video. So what is an outlier? Number one, always do scatter plots and exploratory data analysis. In many videos before, I have yelled this into the microphone and I will do it again. Just do simple scatter plots for your data. It's the simple act of looking at the shape and pattern of your data that can tell you a lot. Doesn't matter how complex a model you plan on building in the end, whether it's some support vector machine or you're doing some principal component analysis or a multiple regression model with a bunch of variables in it, always just do simple scatter plots to start. That will tell you a lot right off the bat. Now, sometimes when you do that, a point or points just don't look right, and they seem kind of out of place, like that blue diamond we saw in the previous slide. For at least one of your variables, a value can appear out of the norm or extreme. So you have this data point that's out kind of by itself. And it's very important to look at what that might be. A point or points may have an extremely large residual value, even though it is within the range of values for that variable. So if you look at the scatter plot, it may not look quite out of place, but when you fit a model on top of that data and then look at your residuals, all of a sudden one of your points or a few of your points have very large residuals, and therefore you have to go back and look at those as potential outliers. Now, a point or points can influence the regression line, pulling it in the direction of the outlier. So wherever that outlier might be, it can actually affect the slope of the line. Or a point or points just fall outside the general pattern of the data. So the vast majority of your data fits a certain pattern, but then you have a point or a few points that are way out of that pattern for some reason. Those are worth looking at. Any of these situations could be a potential outlier, and we have to look at them, find them, and then figure out what's going on with those points. So what is an influential observation? Now, an influential observation, it may be an outlier, but not necessarily so. It could be a value of the independent variable that is far outside the rest of the values for the data, or it could be a value of the dependent variable that is far outside the rest of the values for the data. Or it could be a combination of those two factors above. An influential observation can be within the range of the data and not be an outlier per se. So influential observations, and of course outliers also, can dramatically change the regression output and even change the slope of the regression line from positive to negative or negative to positive. It could also change the model significance or anything else related to that model. They can also change the standard error of the model, and we'll see that as we go forward. So now let's look at these things graphically. So here is our scatter plot and regression line from before. We see our blue diamond here in the upper right. Now let's sort of do some checks on what we talked about in the previous couple slides. First, let's ask ourselves, does our blue diamond here in the upper right fall within the range of our x variable here on the x-axis, our independent variable? So we can go put a box around that. So does that diamond fall within the range left to right of our independent variable? Well, yes, it does. Because we can see that there's actually a data point even further to the right than this blue diamond. So it fits within that range. Nothing too worrisome there. How about falling within the values of our dependent variable on the y-axis? So we'll put a box around those. So does that value fall within the range of the rest of the values? Now notice, it's the only one outside of that range. This is a problem. Every other data point fits within that range. The only one that's outside of that sort of box is the blue diamond. So that should be worrisome. Now, thirdly, how about the general pattern of our data? So here's the general pattern of our data here in this color. Does it fall within that pattern? No. So we looked at whether or not this point fit within the range of our dependent variable, our independent variable, and the pattern of our data, all three. Now, it was in the range of our independent variable, but not the other two. Therefore, we should keep this in mind because it might be an outlier. So here are some questions to ask, some real-world questions. Was there an error when recording, entering, or coding the data? What we might call a fat finger error. So for example, a data set indicates that a student received a 40 on a test when in fact it should have been entered as a 70. So if you look at most keypads, you'll see that the 7 and the 4 are close to each other. So if you're typing in data really quickly, it would be really easy to hit 40 instead of 70, and we'd call that a fat finger error. Do the outliers or influential observations suggest a different model should be used, such as a curvilinear model? For example, financial yield curves, if modeled using linear regression, can create outliers where the curve bends. So think about it. If our data is in a curve shape, but we force a linear model on top of it, we're probably going to generate points that have very large residuals because we have a line on top of a curve that's not going to fit very well. Are there questionable observations in the population we're looking at? For example, let's say we're modeling work experience versus salary data. Now in that, we included the executives that have very high salaries. Well, what's going to happen on our scatter plot is we're going to have the vast majority of the workforce sort of in the middle of our scatter plot. Then we're going to have executives that have multiple times the salary of a typical worker out probably far to the right and up in our data. So if we are really looking to model work experience versus salary data, maybe we should exclude those executives. They are valid points that are in the data set just by random chance. That's completely possible. So we could have these points in there that there's no fat finger error, the model is linear, or the observations aren't questionable, and they're just there due to random chance. And of course, if you study statistics for any amount of time, you know that that just happens sometimes. So next, let's look at some graphs and computer output. So here's the model we used before that has our outlier in it up here with the blue diamond. So you can see the same regression equation and the same R² value we had before. So now let's go ahead and look at the full regression output for this model. Okay, so here's the full computer output for that model. We're not going to go over everything in this, just a couple things. So first look at the R² and adjusted R². We can see that's the 0.2962 we saw in the previous slide, and the 0.2719, that's the more conservative adjusted R². But either way, we can see that about 27 to 29% of the variation or the variance in the dependent variable is explained by the independent variable. So about 30% of the variance in the price of the car is explained by the number of miles it has on it. Next thing to take note of is the standard error. Remember, in general, the standard error is a measure of how well the data fits around the regression line. So a smaller standard error would have data points that are closely packed into the regression line. A larger standard error would have points that are further away from the regression line. So the standard error in this model is about $4,100. And it is in dollars because our dependent variable is in dollars. Now it's hard to know what that means on its own, but when we compare it to other models, we can see how it will change. So down here in the ANOVA table, we can see that we have an F value, an F statistic of 12.21 approximately, and the significance is 0.0015, going around is 0.002. That is somewhat important because depending on what significance level you choose, if you chose 0.001 as your significance level, then this model would not meet that criteria. However, if you chose 0.01, it would. So again, in these models, you choose the level of significance you are willing to accept, and that's really up to you. But in this case, if we just chose 0.01, then we would conclude that this model is significant. So finally, if we go to the miles variable at the bottom, go to p-value, you'll notice that the p-value for miles, 0.001548, etc., is the same as the significance for the F statistic up above because this is simple regression and they are both the same. So here is a residual plot of our data from before. As we can see, almost all the other data points fit in this nice tight band around 0. However, we have this one point, that was the point we looked at before, that has a very, very large residual. So what we're saying here is that our regression line really gathered up and modeled the other points very well. They fit in this nice band around 0 in the residuals. However, we have this one point that has an extremely large residual, and therefore that's something we need to go look at further. Now, if we go ahead and calculate the residuals for this data set, something pops out at us. If we go down to observation 26, we can see that we have a standardized residual of 4.105. That is a massive, massive standardized residual. We would expect that these residuals, about 95% of them, would be plus or minus 2 from 0. So between -2 and 2. However, we have this one here that is a magnitude 4.105. Therefore, we would conclude that this observation is indeed an outlier. It is well beyond the range of plus or minus 2, and it's well beyond the range of the other standardized residuals. So there is our outlier. So now let's take out that outlier and do the analysis over again very quickly. So interestingly enough, you can see that all of our data points fit around the regression line very nice and neat. If we look at our equation up above, now it's telling us that our coefficient is negative 0.1349. Now it's saying that for every mile we drive the car over time, it decreases its value by 13.5 cents, which is different than our previous model. So this model actually is telling us that our car loses value quicker than the previous model. Now look at the R-square, 0.6909. What this is saying is that almost 70% of the variation in the price is explained by the mileage on the car. Now, if you remember the previous model, it was a lot lower than that. So we'll compare these side by side. But removing that 1 point, just 1 point, made this difference. So here are the statistics for that model with the outlier removed. Now we have an R-square of 0.6909, like I said before. The more conservative adjusted R-square is 0.6798. So again, we're up in the close to 70% of the variation range as far as being explained. The standard error in this model is 2,454. Remember, the standard error in the first one was over $4,000. So it almost cut the standard error in half. Removing that 1 point cut the standard error in half. And it makes sense. Remember, the standard error is saying, how well do the data points fit around that regression line? And with the outlier removed, the rest of the points fit around there very nice and neat. So if we go down to the ANOVA table, our F value there is 62. That's very, very high. And of course, you can see that our significance level is 7 zeros and a 1. So it is very, very a small number. So here is a model comparison chart. So with outlier and then without the outlier. So the outlier removed. So let's go on the R-square here. It was 0.296, and then it jumped to 0.691. These are slightly rounded. So as you can see, that by removing the 1 point, the 1 outlier, the amount of variance explained in our dependent variable more than doubled. It more than doubled by removing that 1 point. The adjusted R-square, the same thing, 0.272 to 0.680. The standard error was almost cut in half. So 4,093 to 2,454. By removing 1 point, we cut it in half. The F value went from 12.21 to 62.57. And of course, the significance value went from 0.0015 down to almost zero. Not quite zero, there's many zeros there than a 1, but you can see it's less than 0.000. And then, maybe more important than anything, if we're making a model to explain something in the real world, our model should be obviously accurate, and it can have real world ramifications. With the outlier, we were saying that our car lost value for every mile it was driven of a little bit over 9 cents, so $0.0937. Now we take the outlier out, and now we're saying that our car loses value of 13.5 cents for every mile it is driven. Now I know we're talking in just cents of a dollar here, but going from 9 cents to 13.5 cents is basically, about an increase of 50%. It's a 50% increase in our predicted loss of value in our car for every mile we drive it. And in the real world, that is a big, big difference. So all we did, we removed 1 outlier and it changed our model that much. That's how important it can be. So here's what our regression line looked at with no outlier. And then when we add the outlier back in, that's what it looks like. See how much the outlier pulls the blue line upward. It significantly changed the slope of the regression line. Just that 1 point. It's like a star in space, that anything that gets near it kind of gets pulled towards it. You can think of the outlier like that. It's pulling this regression line upward and totally changes the regression slope, the coefficient, until it changes the slope of that line. So with the outlier, you can see it in the upper right, this is a model of our confidence interval in the dark pink and our prediction interval in the lighter pink. Now, if we remove the outlier, it looks like this. Now don't be confused. The dot is still there, but the dot is not being included in this calculation. So look at the difference between the confidence bands with outlier and without outlier, and then the prediction interval with Outlier and without. See how much narrower it is? Just the removal of that one point makes the confidence interval and the prediction interval much, much narrower. So a final teaser topic. We're not going to go into this in this video. This is a teaser for the next video. And that video will be about the concept of leverage in regression. So a data point that deviates a lot from the rest of the points for the independent variable along our x-axis is called a high leverage point. So those points can literally work like a lever, tilting the regression line towards that point. So where I grew up, we had what's called a seesaw. That's the thing you see where one child is on one side, another child's on the other side, and it kind of goes up and down in the middle. So the middle is the fulcrum, and then they seesaw up and down. Well, there are points in regression that can do the same thing to your regression line. Basically, can seesaw your regression line. So the leverage of data point I looks like this. It's represented by h sub I, and it is 1 divided by the number of observations we have, plus the squared deviation of a single point, so x sub I minus x bar, we square it, divided by the sum of the squared deviations of all points. Now, if we make a decision if a point is high leverage or not, we have to have some sort of decision variable. And it goes like this, where p is the number of independent variables in our model. So h sub I greater than 3 times the quantity of p plus 1 divided by n. Just simple algebra, it's nothing crazy. That is the decision value. So if h sub I that we calculate over here on the left for each point is greater than this decision value we have here, then we say that that value has large influence, it has high leverage on the simple regression analysis. And we'll look at that more in the next video. Okay, so that wraps up this video on simple linear regression, namely outliers and influential observations. Again, it's not something that we can ignore. If we want to be really good statisticians or business people or data scientists or whatever else, we have to take into account observations that can have a large influence on our model. That can cause classification errors, that can cause all kinds of things when we're building a model. We can make imprecise predictions with our models. So it's very, very important to go and look at the scatter plot, look at the residual analysis, and figure out if we have any outliers and or influential observations. So thank you for taking the time, which is your most valuable resource, and spending it here with me, learning about these topics. So hopefully I will see you next time, and until then, take care. Bye-bye.